Our next talk will be given by Vanja Paunic, who is currently a data scientist in the Algorithms and Data Science group at Microsoft London, and is working building machine learning solutions for external clients utilizing Microsoft's AI cloud platform. Her talk will present an overview of Microsoft DNN technologies for computer vision, describing both how the technology works and how Microsoft is making this technology available for outside users to build their own custom computer vision solutions. So without further ado, I shall now proceed to give the talk to Vanja. Also, don't forget to use the code DSC.network/Q/A Tesla. Thank you very much.
Hi, everyone. My name is Vanja Paunic. Thank you for introduction. That was going to be my first slide. So I'm Vanja Paunic. I work as a data scientist for Microsoft, and I work on building machine learning solutions for Microsoft customers. And so some of this talk came about, from the experience working with customers in the computer vision use cases. So we will, I'll briefly introduce some concepts in computer vision here, with some common computer vision tasks we work with. Then I'll follow up with how deep learning is applied in computer vision as a setup to how we can easily customize pre-trained deep learning models to new computer vision problems. Then I'll introduce some Microsoft computer vision services that are sort of aimed at AI developers to more easily develop computer vision solutions from pre-trained deep neural networks. So let's look at some of these very common computer vision tasks. So these are some of the common ones, not meant to include all computer vision tasks here. The most basic question that we see out there with customers is image classification use case. So this is a problem of identifying, given a set of images, identify a label for the image. A label could be a scene, or it could be such as in this example, is there a deer in an image or not? So as long as the object or the label you're looking for is anywhere in the image, this is sufficient to solving the image classification task. Object detection goes a bit further, and it asks for not only is there an object that you're looking for in an image, but does it, where exactly it is in the image. So it asks for this bounding box of the object that you're looking for, so the bounding box of a deer. Image segmentation goes then even further to ask not only give me the approximate coordinates of the object that I'm looking for, but give me exact pixels that constitute that object in the image. And then finally, we often see image similarity problems where given a query image and the set of other images, give me images that are most similar to my query image, and rank them in some order. So before deep learning came about, these computer vision problems, let me just bring everything up. These computer vision problems were solved using pretty traditional machine learning approaches, where we create what is called a feature descriptor, which is usually some sort of mechanism for extracting features that describe that image. So very common example of these feature descriptors are hog features or histogram of oriented gradients, where you're really just looking to describe these sort of edges in the images, so that once you, for example, in the bike image here on the left, you can see the features extracted for that image in the right. Where is the, right here. And sort of these features now help you identify sort of the edges in the image to further help you identify what object is on the image. So this technique is commonly used in the object detection scenarios. This and other common computer vision approaches before deep learning came about all have sort of a two-step approach, where you first create the features, then you feed those features into a traditional machine learning model, such as this SVM classifier. So it's so any new given use case, you are tasked with sort of solving these two problems of finding the appropriate feature extractor and then finding the appropriate model for that problem. And so it can be a very tedious task, even though these approaches have been pretty successful up until about 7-8 years ago. So when the deep learning came about and was in particular introduced in the computer vision field about 7-8 years ago, it sort of abstracted those two processes away and really implemented the feature extraction process as a part of the model training process. So as you can see, we feed, this is a typical conceptual view of the deep learning architecture, most commonly used in computer vision, called convolutional neural nets, where we feed an image into a deep learning model. And we, at the end, we sort of give the image labels to the neural network, and the neural network then, through the process of training, learns how to associate image pixels with the labels. And so most commonly in these architectures, we have initially several convolutional layers, followed by several fully connected layers. So convolutional layers really, on a high level, learn the features that are present in the image. So initially, in the initial layers, the convolutional layers learn the low-level features, such as shown here, color fields, lines, edges, and so on. As you go further down through the network, you'll see that the network in the intermediate layers learn a little bit higher features, such as corners, contours, simple shapes. And then finally, if you look towards the end of these convolutional layers, you'll see that the network is able to learn object parts such as wheels, faces, windows, etc. So at the end of the convolutional neural nets, you usually sort of combine all of these features together into fully connected vector representations of features, which then are passed to the final ultimate layer to predict the class of the image. So as you can see, this whole process of feeding, starting from image in the form of pixels through the label is simply one process, and it requires one training. You're not necessarily separating the parts of featurizing an image and then training a model. So one caveat of using deep neural nets in general is that they require very large data sets. So they typically have many parameters that need to be trained. So in order to make them generic and generalizable to new problems, you typically need very large data sets, which a lot of companies actually, or a lot of users don't have. So the research community has been over years gathering large data sets of images and annotating them through crowdsourcing. So now this ImageNet dataset contains more than 10 million images, more than 22K labels, and it's a very comprehensive and generic image dataset covering extremely wide ranges of labels. So why is this important? I'll mention in a little bit. But I should say that in addition to the data set, the ImageNet also conducts a competition, a yearly competition on a variety of computer vision tasks, one of which is ImageNet classification accuracy, or error rate in this case. And as you can see, the error rates have dropped from about 28% down to actually more than, or less than 3% now. I don't know the exact number, but I know in 2015 it was 3.5%. And this is really dramatic improvement. 2012 is the first year when the deep learning was introduced in, or when the deep learning model was used in this competition with a network called AlexNet. And as you can see, the drop in the error rate here was very significant. The progress further on through the years has even been even more dramatic, I think, as the researchers have been learning and finding out better ways to define these deep architectures for the computer vision problems. So why is this important? Ultimately, we want to see how we can use these pre-trained deep neural nets for new tasks, new computer vision problems that we have. And so having these large data sets that we can use to train our deep neural nets and use them on new problems is the way we can go about solving our computer vision problems. And so what are the different ways we can use pre-trained deep neural nets in our solutions? So we can simply use a pre-trained deep neural network as a featureizer. So we can say, I'll just use my small data set that I have, I'll pass them through the deep neural network. I'll strip off the last layer that does the ultimate classification, and I'll collect the features from the penultimate layer of the deep neural network. And I'll use these features in whatever classifier I want. To produce my own features, to produce my own labels. This has been found really successful in cases where you're, for example, using ImageNet, pre-trained deep neural net on ImageNet datasets, and you have images that are pretty similar, pretty similar to a subset of ImageNet images. In that case, this would be a very good, you would be able to achieve pretty good accuracy using this approach. However, if ImageNet, for example, does not contain the label of your images, or if your images are not representative of what's available in the ImageNet, you might need to do something called transfer learning, which is, you can think of it as taking a pre-trained deep neural net, freezing some of the initial layers so that the parameters of the network don't change as you're training, and then really just retraining the last couple of layers of your neural net. So what that allows you is to still use all of the lower to intermediate level features that are captured in the earlier layers of the network, and then just tune your network to learn from the images that you're feeding into it. So for example, if deer wasn't present in the ImageNet, you would simply retrain these last couple of layers to retrain them on your images. And this has also been shown to produce very, very, very good performance without having to use large sets of data, or without the need to have many images to train with. All right, so this slide sort of summarizes some of the findings that are found on using pre-trained deep neural networks in new computer vision tasks. So the takeaway here is that the left bar here shows the performance of the state-of-the-art computer vision model, and the rightmost bar shows the use of transfer learning in computer vision, and the accuracy sort of across a wide range of not only computer vision tasks, but a wide range of machine learning tasks is improved by using the transfer learning. Or if not improved, then at the same sort of on par with the state of the art in that category. All right, so how can we, in some of these use cases that we had at the beginning, image classification, object detection, and image similarity, how can we use pre-trained deep neural nets? So in this was a quick example we did for our internal workshop. We wanted to use to test out deep learning on a pre-trained deep neural network. We got some images that are not from ImageNet. We used Bing search to get hundreds of random images of deer. And then we used thousands of images from ImageNet that are not deer. And then we used transfer learning to see how well we can do. And initially, the findings were really good. The accuracy was about 93 or 4%. However, we found that through transfer learning, we got a particular false positive with a forest scene being identified as a deer without even having a deer in it. So what we did is we basically used active learning to include some more true negatives in our data set from the ImageNet that do have the forest scene in them, but no deer, so that we can sort of improve the performance of the algorithm. And this boosted up the performance to something like 98, 99%, which was really good. In the image similarity case, the transfer learning can be used in this particular case, or in this particular way. So in image similarity, the problem is, given a query image, let's say this one, give me a set of images that are similar to it. So essentially, we want to compute some sort of distance between images. And a way we could do that is we could, again, use deep neural nets as featureizers. So we can run this image through the featureizer, through the network, to obtain a numerical vector. This is some random image taken from the set, and also we can obtain the features here for that image. And then we can use some distance-based or similarity-based metric to compute images, or to compute distances between these two images so we can rank them, or some more intelligent way of doing, I guess, similarity computation. But the point being that you can use very effectively deep neural nets to represent these images as numerical vectors, that it allows you to then compute similarity more easily. In object detection, the way transfer learning is used is in the following way. In object detection scenarios, just to give you some background, usually the most popular approach is called faster RCNN, which combines two networks. It combines the CNN network initially to obtain the feature map or the features of the image. And then it also combines this region proposal network, which really is a way for, which really is where in the network you select some proposals of, some region proposals in the image that you think are good candidates for where your object is. So in an example where we had a deer in the image, and we were concerned with object detection, we would generate some sort of bounding boxes candidates for what we think might be a good place to look for a deer. So this is this region proposal network, and it's sort of used in combination with the CNN that creates the feature map, and this whole network can be fully trained, jointly trained to produce the final bounding boxes of the objects that you're looking for. So in the transfer learning here, in this case, we can simply use the CNN here once to compute the feature map, and then really just retrain this part of the network to allow us to identify objects in the image. So what has Microsoft, I work with, with Microsoft, and I work with customers, so we always look for some internal services that are available that make this process easier. And custom vision service is something that you can use to create pretty accurate computer vision models without much computer vision experience, really. So what it allows you to do, it's really this service that has a web UX that it allows you to upload images, tag them, train the model, and then evaluate the model, and also use active learning to correct some of the mistakes that the model might have made, that then goes back into the training of your model that essentially improves the performance. Let me see. One of the benefits, I guess, of using this custom vision service is that you can train your model in custom vision service, and then you can use the REST API endpoints that it provides you at the end to deploy your service, to call your service for scoring from pretty much any platform. But it also allows you to download your model in the Onyx format, which is this interchangeable format for deep neural nets, which then allows you to really deploy your model anywhere on edge devices or really anywhere. So I'm just going to show you here, walk you through a couple of slides that show how easy it is to create this service. And I'm not joking when I say it's really just a couple of minutes. You can create a project here, name your project. And then you can select a domain here, which really is an attempt to match your data with the best pre-trained deep neural network. Because all that custom vision service is doing, it's using a pre-trained deep neural network in the background to score your data on, and to use transfer learning to tune that model a little bit using your data. So you can really start with 30 images or so. So if you have, for example, a data set of food images, it will select a model that's particularly specifically trained on food images so that your data matches the pre-trained model better. Once you do this, you'll get this sort of empty space here, which allows you to add your images. As you see, there's no images here at this moment, but in the next slide, I've uploaded some images of Brontosaurus and Stegosaurus dinosaurs, and basically you can use this UX to tag images and to assign the labels to them. Finally, you click, I don't know if I can see this button, but there was a train button somewhere. Finally, you can click this train button and it will tune the pre-trained neural net in the background. And it provides you immediately with some feedback on how well your network is doing. So these are some performance numbers such as precision and recall. But more importantly, you can look through the images and their assigned labels and the scores that the model produced for them. And you can then correct those labels using active learning sort of to then push those images into the new training iteration. As you can see, I have a couple of iterations here. So you can then produce a new training iteration which will hopefully give you better performance as your network is then more sort of tuned to your data set. This is a very high-level API. You basically have very little control about, selecting a different pre-trained neural net, or changing the architecture slightly, or deciding what layers of the network you're going to train and what layers you're going to freeze. So it just sort of allows you to do this quickly, test it out maybe on your data set, and if you're happy, you can deploy it, use the REST API endpoints for scoring. But if you want a bit more control and sort of be able to dig into the models that you're using, Microsoft has this Microsoft Cognitive Toolkit, formerly known as CNTK. This is really open source, commercial-grade deep learning toolkit. So most of you must have heard of TensorFlow. This is Google's version of CNTK. Internally in Microsoft, CNTK is used across many core Microsoft projects, such as Bing, for example. So it's really sort of battle-tested, commercial grade quality. It's easy to scale, and the speed is incredible. So a lot of engineers in Microsoft are using CNTK for commercial grade deep learning. But it does involve, it's a lower level API, so it doesn't involve some knowledge on deep learning, what you're doing with your data, how you're, you can, for example, you do all sorts of tricks with your data sets to improve the performance, such as you can improve your training data by augmenting images, flipping them, rotating them, and so on to make your models more generalizable and more stable. All right, so finally, these are some resources. So these are just basically links to those two services I described. And now, if you have any questions, here's my email address. But I'll be happy to answer questions here as well. And thank you for listening.
Thank you, Vanja, for this brilliant talk. Going swiftly to the questions at hand. The first question is incremental learning supported somehow? And how can we say that there is a need to retrain a model from scratch?
Incremental training, so I'm going to assume that that's basically retraining your models using new data. So I would say if you're happy with the performance of the model using transfer learning, so retraining the last couple of layers of the network, then you're all set. It's all about the performance goal that you're trying to achieve. When we're working with the customers, they often have some goal in mind. So if it's 95% of accuracy or so, then we're sort of aiming to achieve that, to match that. But if you're unhappy with your performance, then you can, I would say retraining the entire network is a really difficult process because you ultimately need lots of data to retrain it properly, to make those parameters, to not overtrain your network, for those familiar with machine learning. But lots of data is not easy to come by, and often the customers that we work with have smaller data sets, so transfer learning is really the best we can do. But yeah, I would say if you're not happy with the performance, that means enrich your data set with new training samples, think about other architectures. That's the way to go with.
Now we have here for photo classification. So what would you use for high altitude aerial photo classifications of, for example, boats, ships?
Ah, okay. So there is a I would say whoever asked this question, maybe come talk to me afterwards, because there is a really cool project going on with aerial photography classification in Microsoft, and I have some resources to point you to. They might have a GitHub account. I think they have GitHub that I can point you to, but I haven't worked with aerial images, so I don't know, the specific, the particularities of these images and what models would be best to use. But I can point you to some resources.
As always, you're invited to talk to us speakers
Yes.
privately as well to get more in-depth analysis here. So in your experience, are low and mid-level features from ImageNet pre-trained models reusable for different kinds of problems? Let's say pixel segmentation.
That's a good question. Let me think. This is the approach actually that's commonly used, as I described in the object detection transfer learning scenario, where you use a CNN to generate a feature map and then really just train the region proposal network part. So given that that's sort of a common practice in using object detection, transfer learning in object detection, I would say that, low-level features that depends on your images. If your images are really sort of, particular, I've seen images of, when you have industrial pipelines and there's a camera taking an image of like a chip or something really small that's not necessarily included in ImageNet and is not representative, then I would say, you could probably do better with trying to train on your data set, but generally, low-level features produced by ImageNet pre-trained models are sufficiently good.
Thank you for this answer. So on a pre-trained model, is there any other solution except for the one inserting random images for the minority classes?
What was that?
So on a pre-trained model, are there any other solutions except inserting random images for the minority classes?
I see. I don't see what the problem is with trying to sort of picking negative classes randomly, because you do want to. I guess if you do have a classification problem where you're classifying between two classes, deer and cat, and you're not really concerned with anything else, then you don't necessarily need to enrich the negative class. But when you're, looking for deer versus anything else, then I don't see what the problem is with selecting random images from the ImageNet or anywhere else, Bing search, Google search, yeah.
Always. So how significant are adversarial algorithms in computer vision, given that label data is not that easy to get?
Adversarial?
Algorithms.
Adversarial algorithms, yeah. So I'm not, I know what the adversarial algorithms are and what adversarial images are, but I'm not too familiar. I haven't worked with them. I'm not familiar to answer that question.
Yeah. So going back to the pre-built model, why actually use it? Why use a pre-built model?
Yeah, because it is really good. It is really hard to, given a small. If you have millions of images on your hands, so you can train this a deep learning model from scratch, then by all means do that. But it's typically, customers that we worked with don't have millions of images. So when you have small number of images, you're very likely going to produce parameters of the network through the training that are not generalizable enough for your future data. It's basically hard to train the neural net and learn the parameters using small number of images because the parameter space of the network are so large.
Thank you. Do you use any domain adaptation techniques with deep learning?
Do I use what?
Domain adaptation techniques with deep learning?
No. Other than, as I said, as I showed an example of domain-specific networks, so there are even besides Microsoft, there are all sorts of pre-trained neural nets out there available in open source communities. So if you can find, there are some pre-trained neural nets that are particular for a domain, such as, food deep neural nets that I pointed out before. So if you can find a neural net that's pre-trained on a large set of data set that best describes that domain, I would say go for it. But beyond that, I haven't used anything else.
Shifting a bit to the speed of recognition. So how fast is it in terms of recognizing things? And could it be possibly used in real time, for instance, with automated cars and so on?
Yeah. I mean, there are all sorts of systems already put in place out there that are the real-time face recognition systems. For example, as you're approaching the door, will the door open automatically for you if it recognizes you versus not? So, these systems are definitely tuned to the desired performance for the real-time systems.
Okay, and the final question here. Can you do an analysis of existing conversion filters activations in pre-trained nets to drop filters not relevant for transfer problems, therefore reducing the network complexity?
You can do that to some degree. I know you can, for example, change the size of filters in convolutional networks to adapt your network to image sizes to different image sizes than what the network was trained for. I can think of that example. But yeah, to some degree, I would say you probably can't do it arbitrarily. Yeah.
Thank you. This was our final question for this talk. Thank you, Vanja, again. And on behalf of the conference, I would like to give you this certificate of appreciation as well.
That's sweet. Thank you.
And I would also like to thank the audience for such interesting questions.